Okay, let's see. Hi everyone. So today we are going over force and acceleration. This is going to be pretty quick. We're going to do a couple example problems on how we can use force to find acceleration. So our first example is a hockey problem. We're going to calculate the magnitude and direction of the acceleration of this 300-gram hockey puck. So what we'll do first is we will look at the forces, right? We have F1. Let's get our givens somewhere. Let's put them up here. So we've got F1 equals, what is it, 5 newtons? Yep. 5 newtons, and F2 equals 8 newtons. And that is at, that is 20 degrees below the x-axis. And this is at 60 degrees above the x-axis. Right, so those are the givens that we've got. Now, what we want to do is we want to look at the magnitude and direction of the acceleration. So let's talk about first, what is the magnitude and direction of the acceleration? Well, the direction of the acceleration will have to go in the direction of the unbalanced forces, right? So we want to look at the summation of forces to give us the direction of the acceleration. We also already have the mass. Mass is 300 grams, which is 0.3 kilograms. So if we want to find acceleration, our acceleration would simply be our summation of forces divided by the mass that we have. So we need to find that summation of forces. And it'll be in the same direction as the summation of forces. So let's, one way we can do this, you can split it into the x and y summation of forces to do that, but that would give you two different accelerations, acceleration in the x and acceleration in the y. We don't really want that. What we can do to get the overall acceleration real quick is split this into vector components. So let's do that. If we have F1, okay, if that is 5 newtons at 20 degrees below the x-axis, the I component would be 5 times cosine 20 I hat. Now let's look at this right here, right? Here is our x, or our I hat. Here is our y, or j hat. So if this is our theta, right? I guess they've already got it right there, really long arc. That's our theta. We'll use cosine or adjacent to get the x, and we'll use sine or for the opposite, or the y. All right, so F1, 5 cosine 20 I hat. Now this would be minus because that is negative y, right? It's going down below the x-axis for that one. Minus 5 sine 20 j hat. Then for F2, okay, it's going to be very similar, only we're going to change the magnitude and the angle, but similar concept. 8 cosine of 60 in the I hat, plus, this time because it's going above the axis, plus 8 sine 60 j. Okay. Now, before we do this math, we don't want to add 5 cosine 20 and 8 cosine 60. We're going to want some actual values to those. So I've already done the math on those. Oh, no, I haven't. So let's look at that. So a lot of calculator work. I'll skip through this. All right, we're back. So I did the math real quick off camera. We've got 4.7 I hat minus 1.71 J hat. And then for force 2, we've got 4 I hat plus 6.93 J hat. So what we'll do is we'll add those together. We have 8.7 I, and that will be plus, let's see, we have 2, is that 5.22? Let me double check. Yeah, 5.22 J hat, and that is our summation of forces vector. So that is the vector that we're looking at. Now, we want the magnitude of this vector, right? We can't take that vector and plug it in up here and expect to get the magnitude of the acceleration. So we need the magnitude of forces to get the magnitude of the acceleration. We just wanted the acceleration vector, it'd be a little bit easier. So to get the magnitude, right, of that force vector, we'll do Pythagorean theorem, 8.7 squared plus 5.22 squared. And that comes out to about 10.15 newtons. Oh wait, that is not our answer, so I'll just circle it. That's an important component there. All right, now, we've got our summation of forces. Now we can plug that in for our acceleration, right? Let's get it right here. Acceleration is summation of forces divided by mass. So we have 10.15 newtons divided by 0.3 kilograms, and that will give us 33.83 meters per second squared. Right there, okay? So that's the magnitude of our acceleration. Now we need the direction of the acceleration. And I mentioned before, the direction of acceleration will be the same direction as the summation of forces. We come back up here, we're thinking Newton's laws, right? If you want to talk about acceleration, you have to talk about unbalanced force, right? So wherever that unbalanced force is, the summation of forces, that is going to be the same direction as the overall acceleration of the object. So let's just find the direction of this force, right? So we start here, we've got 8.7 in the I direction. We've got 5.22 in the J direction. And we've got a hypotenuse of 10.15 theta. Now, most common way to do this is to use tangent. Since we have all three sides, you could use cosine or sine also, but most common way to do this is a tangent inverse. You would do opposite over adjacent, so you've got 5.22 divided by 8.7. So that theta comes out to be about 30.96 degrees. And you would tack on above the x-axis to give it that true direction. Okay, so that is a method that we can use to calculate the acceleration and the magnitude and direction of it with the given information. Now we used a vector method here. Next, we will use a slightly different method. Instead of using vector methods, we'll use x and y directions instead. So accelerometers, right? A simple accelerometer is constructed by suspending a mass m from a string of length L that is tied to the top of a cart. As the cart is accelerated, the string mass system will make an angle theta. So step 1, draw this and add force arrows for the two forces acting on the hanging mass. So, I don't have an extra slide here. Okay. So we'll drop that down a size. So what we'll do first, right, we need to draw this. So we've got a hanging mass, right, M. it has one vector mg straight down, right? That is your force due to gravity vector. And then we have some tension vector. I'll put that arrow on the other side. Tension vector there. Now, the angle theta here, right? So usually we put things relative to the horizontal, but this time we'll do relative to the vertical. And the reason we're going to do that is because if this were at an equilibrium state, that string would be vertical, right? Now, as that object starts to move, it will deviate. It won't deviate horizontally. It will start deviating vertically. So that's the angle we're worried about. So theta will be from the vertical, okay? Now, those are the two forces that are acting on this. mg wants to pull it down, and the only other thing acting on it is the string, right, of length L, and that is the tension off at an angle. So next, number 2, assuming the mass of the string is negligible, derive an expression for the cart's acceleration in terms of theta. And substitute away as many other variables as you can, but we have to have theta. So let's see, we want to use summation of forces equals ma. Must sneeze. So what we'll do is we'll start with summation of forces equals ma, right? We'll separate that into the x and y dimension. Now in the y, okay, that's where we have mg. There is also no acceleration, right? It's accelerating in the x to make that angle there, but there is no acceleration in the y because everything's going to cancel out. So let's write this out. We have tension, and this will be cosine theta. I'll explain that in a minute. Minus mg equals 0. So if we look up here, usually we use cosine for the x and sine for the y because we're measuring our theta to the horizontal. But as you can see here, our y is adjacent to the theta and our x is opposite. So we will use sine for x and cosine for y. So back down here, we've got t cosine theta minus mg equals 0. Let's go over to the x. Here, all we have is t sine theta equals mass times acceleration in the x. Because acceleration in the y is 0, that all goes away. Now, we want to solve for acceleration, right? Derive an expression for the cart's acceleration in terms of theta. So that acceleration is right there. That's the acceleration we're shooting for. So if we solve that, let's say we have t sine theta divided by m equals a in the x. Done, right? But it did ask us to solve this in terms of theta and substitute away as many other variables as possible. So what we can do on the y side, we can solve for tension and plug that in, and that will help us cancel things out. So if we solve for tension, right, tension would give us mg divided by cosine theta, right? Add your mg, divide cosine. If we put that over here, see what would we get? We would get mg over cosine theta times sine theta divided by m, right? Now the m's will cancel. Sine over cosine can simplify to tangent. So our acceleration can also be described as just g times tangent theta, which seems a lot more simple than t sine theta over m. This also shows you that instead of using this right here, we can see that the tension doesn't actually matter to the acceleration, and the mass of the object again doesn't actually matter to the acceleration. The only thing that matters is the g on the gravity in that area and the theta that string is moving. So this is an experiment that you can do, and I don't recommend you do this alone or without aggressive planning to make sure that this is safe, but this is something that you could do in a car. If you hang a mass on a simple string in your car, and as you drive, that mass will start to move, right? And you can measure that angle if you had a protractor. Now you would need a driver completely focused on the road and a second, maybe even a third party taking measurements and then recalibrating the mass, holding it still after you make a turn or something. But this is something that you could do to find the acceleration. If you just have g and the theta, you can find your acceleration of an object if you can do this experiment. Okay, so that's accelerometers. Last one for the video, elevators. So this one, we're going to look at this scenario over here, right? We have a girl and a fish in an elevator. Who doesn't want to weigh their fish while riding the elevator? That makes you really popular on your elevator rides, I'm sure. So there is a fish hanging from a scale, and the girl is standing in the elevator. We have a positive acceleration going up. Later in the problem, we'll manipulate that. And then we have the forces on the fish over to the side, tension and mg. So let's look at the questions that we have. First, which passenger feels normal force and which feels the tension force? Well, that fish off to the side is hanging, right? Is hanging from the scale. So that will have a tension force up, and then the girl standing in the elevator will have the normal force pushing up. But very similar scenarios, mg pushing down, and then there is a positive force balancing that up. Now, we do get some information in the next sentence. The fish on the metric scale has a mass of 1 kilogram. So we now have a given, right? Mass is 1.0 kilograms for the fish. So it seems like we'll be focusing on the fish. What does the scale read when the elevator is A, at rest, B, accelerated up at 5 meters per second squared, C, at constant cruising speed, D, slows down at 5 meters per second squared, nearing the target floor, E, accelerates down at 5 meters per second squared to return to the lobby, and then F, everyone's fantasy that everyone wishes would happen to them. The elevator breaks and is in free fall. So I hope this doesn't give you anxiety, but we're going to work through these problems step by step. So first, it asks what the scale reads. So let's talk about this scale, right? We've got a fish, and we have a down force of mg and an up force, curvy line there, of tension. Now, that scale is part of a Newton third law pair, right? If we look at that scale, the scale also has tension pulling downward from the fish. And however hard that fish pulls on that tension, that's going to manipulate the reading on the scale, right? So what we want to find here is the tension. That's going to tell us what the scale reads. So let's look at that. If we have summation of forces equals ma, how would we find that tension? Well, we have T minus mg equals ma. If we solve this, you could add that over. You'd have ma plus mg, and you could even simplify that further and say that's m times a plus g. Okay, so that a seems to be, that is the elevator acceleration or the system's acceleration. Okay, and then g will be a constant 9.81 meters per second squared. Now remember, g itself is not negative. it should be negative, and we had it negative up here, but that does not mean that the variable g is negative, right? You got to follow your signs. Here it shows in this equation, we are going to add g. So that doesn't mean that we need negative 9.81 there. It's going to be positive. I know this doesn't seem intuitive, but believe me, I have to follow me here. So we've got t equals m times the quantity a plus g. So let's look at these step by step. At rest, right? At rest, what is the elevator doing? Well, at rest means the acceleration is 0, right? So tension equals 1, the mass of 1 times 0 plus g, which is 9.81. So you would get 9.81 newtons if you're just sitting still in the elevator, right? That is the true weight of the fish without any manipulation. Just sitting at rest, 9.81. Now part B, okay? What happens when the elevator is accelerated up at 5 meters per second squared? Well, that tension, now we have 5 plus 9.81. That's going to register at a 14.81 newtons. Now, let's think about that, right? So as the elevator goes up, that fish has a little bit of inertia, right? So it wants to stay put, but the scale starts taking off without it, right? So that's going to pull a little bit harder on that scale. It's kind of like a relativity thought experiment, right? So the scale tries to take off without the fish resists the motion. So during that acceleration of 5 meters per second squared, until it gets up to its cruising speed, that scale will actually register a little bit heavier than it should normally. Now part C, at cruising speed. So at cruising speed, again, acceleration is 0, right? There's no change in speed. It's a constant speed. So then the scale returns to 9.81 newtons. So at rest or at cruising speed, when there's no acceleration, you'll see the true weight of the fish on that scale. All right, part D, next. The elevator is now nearing the target floor, and it starts to slow down at 5 meters per second squared. So that means that our acceleration is 5 meters per second squared. But it's slowing down, right? So to slow down, you have to have a negative acceleration. So we can't forget that this will be negative 5. So because that's going to be important here in our calculation. T will be 1, and that's negative 5 plus 9.81. So now the scale registers at 4.81 newtons. And now let's look at this diagram here. Let's get rid of that. Right? So in this diagram, we have the elevator, right, is slowing down. But like we said before, the inertia of the object, it might be easier to think of the girl than the fish here. Similar scenarios, right? You would be looking at the normal course instead of the tension. So as that elevator starts slowing down, right, you feel a little bit of weightlessness. And that is due to this effect here because of that acceleration. So as that elevator is cruising at a constant speed, the girl is moving along with it. But to slow down, the elevator in that reference frame is almost like the elevator is dropping away from the girl because it needs to slow down. So the girl's inertia wants to continue at that constant speed, but the elevator needs to slow down, so the elevator starts moving slower than the girl. So the girl kind of lifts off of the floor, and the floor technically, if you look at that reference frame, it looks like the floor would be pulling away from her, right? Similar to the fish, but the scale, so here, the fish, right, is hanging from this scale. So the fish wants to keep going, but the scale doesn't. So the fish will actually give some slack to the scale, it's a little bit more complicated of a thought experiment, but so that's why the scale would read less in that scenario. All right, next, part E. The elevator is now accelerating down at 5 meters per second squared so that it can return back to the lobby, right? So it needs to get back to its cruising speed. So our acceleration, right, it is 5 meters per second squared because we're going back down to the lobby. But we are accelerating downward, right? So last time the floor had to accelerate down to slow down. Well, this time the floor has to accelerate down to speed up, but the effect is the same, right? The floor is still going down, so this would still register at negative 5 meters per second squared. So we have the same result. Negative 5 plus 9.81 will give you 4.81 newtons. And this is you have that same effect, right? When you're in an elevator and you're going up and it starts to slow down, you feel a little bit of weightlessness. Then if you're in the elevator and it starts going down, again, you feel that moment of weightlessness. That is due to the exact same acceleration. Now, everyone's worst nightmare, the elevator has broken and it is in free fall. So now, what is the elevator's acceleration? Well, the acceleration is downward, right? At negative 9.81 meters per second squared. So if we look at our tension, we have 1 times negative 9.81 plus 9.81. So it reads 0 newtons. Why does that make sense? Well, if we look again at our reference frame, right? Let's pull the elevator back over. So if we look at our reference frame, right? Everyone in the elevator is now falling. So the floor is falling, the girl is falling, the fish is falling, the scale is falling. Everyone's falling together at the same acceleration. So, and that acceleration, is due to gravity and everything. But since everyone is falling at the same rate, I guess not really at the same rate, right? Because I guess you're falling and accelerating at the same rate. So since everyone is just in free fall, the scale's not going to read anything. Technically, the girl will be momentarily not really touching the ground of that elevator. So there will be. It's a really complex situation when you look at it. So depending on the starting scenario, if it starts accelerating in free fall from stop, like from rest, then that's a real big drop, and that the girl might actually lift off the ground a little bit. Since they're already accelerating downward, that effect wouldn't be as exaggerated. But broken and in free fall, you really would register as weightless because the scale is also in free fall. So that's why the scale would read 0 newtons in that scenario as well. All right, so that's all we have for this video on force and acceleration. Next video, we will talk about tension and all the different ways that tension can get involved in our problems.